In the last few lectures, we had looked at mass diffusion in gases and in liquids. In gases, mass diffusion takes place at a surface when there is a concentration variation across the surface, because on average molecules coming down across the surface originate at a distance approximately one mean free path above the surface, and the molecules going upward originate at approximately one mean free path below the surface, of the order of one mean free path below the surface. The concentration at these two locations are different, and therefore, there is a net flux which is a diffusion coefficient times the concentration gradient according to Fick's law of diffusion, where the concentration gradient is the spatial derivative of the concentration perpendicular to the surface. Diffusion coefficient has dimensions of length square per time, and it is proportional to the product of the root mean square fluctuating velocity and the mean free path in a gas. And we saw that we can get quite good estimates for this by just substituting the mean free path and the fluctuating velocity. In liquids, the microscopic scale is the molecular diameter, because liquid molecules are separated by a distance comparable to the molecular diameter. In this case, the diffusion coefficient is overestimated if you take the product of the mean free path and the molecular diameter. And the reason that it explained to you was because in liquids, diffusion in a very dense packed assembly of molecules is a cooperative process. If a molecule has to move in one direction, then the neighboring molecules have to execute a cooperative motion, so that there is space for this molecule to move. And so, the cooperative motion of a molecule in a particular direction is a rare event, and because of that the diffusion coefficients in liquids are 10 to 100 times smaller than what we would estimate for a gas. And we had examined one way of calculating these is to use the Stokes-Einstein relation for the Brownian motion of a colloidal particle. This relation gives you the ratio of the root mean square of the distance travelled and time. Okay. For a Brownian particle in a fluid, the mean square of the distance travelled is proportional to time, and that ratio is the Brownian diffusion coefficient. Okay. I should note that it is not exactly equal, it is proportional to. Okay. It is proportional to the product of the mean square distance and time. Okay. And there is a proportionality constant which is 2 in one dimension, 4 in 2 dimensions, and 6 in 3 dimensions here. Okay. This is strictly applicable only for when the particle is much larger than the fluid molecules, but it provides an estimate if you use the same molecular diameter as that for the fluid molecules. Okay. So, and we had seen that, okay, we had calculated the diffusion coefficient for a simple molecule such as nitrogen in water, and we got the correct order of magnitude, but numerically it was there was a difference, okay, between what is predicted by the Stokes-Einstein relation and the actual measured diffusion coefficient. Okay. So, the next topic is thermal diffusion. Okay. Okay. Across a surface, I have in a gas, how is the heat flux related to the temperature gradient. Okay. So, this I will call it as this location Z. Okay. Location Z, this is the temperature, and I have a variation in temperature across this. Okay. Across this location, I have a variation in temperature, and I would like to calculate what is the heat flux. The variation in temperature, as I said, the temperature is related to the root mean square of the fluctuating velocities of the molecules. Okay. Fluctuating velocity is the total velocity molecular velocity minus the mean velocity. For simplicity, I will consider a gas in which the mean velocity is equal to 0. Okay. I will consider a gas in which the mean velocity is equal to 0. Okay. Then the total energy of the system okay, for the translational modes 3/2 kBT. Okay. The total translational energy okay, for the translational modes 3/2 kT has got to be equal to half m into v square. Okay. Average value of v square. Okay. So, let me use this for okay, is equal to 3/2 kT. Okay. So, the molecular fluctuating velocities Vrms is equal to 3 kBT by m the square root of. Okay. So, that is the relation between the fluctuating velocity and the temperature. Now, if I have a temperature variation, right, there will be a flux of energy. Okay. So, how do we calculate that energy flux? We do it exactly the same way that we did earlier for the mass flux. The flux of energy, energy is carried because of the physical transport of molecules. Okay. So, therefore, the flux of molecules across a surface okay, times the energy of those molecules is equal to the flux of energy across a surface. The flux of molecules is equal to the number of molecules per unit volume times the velocity perpendicular to the surface. Okay. Similarly, the flux of energy is the energy per molecule times the velocity of molecules across the surface. Okay. In this case, most processes that we will be dealing with are processes at constant pressure. Okay. And for processes at constant pressure, the appropriate energy is the enthalpy. Okay. So, therefore, the energy flux across the surface okay, to be more precisely the enthalpy flux okay, okay, is equal to it is going to be proportional to the velocity perpendicular to the surface. As I said, the velocity perpendicular to the surface, the average velocity of molecules perpendicular to the surface will scale as some coefficient times Vrms. Okay. And the enthalpy flux is going to be equal to the enthalpy per unit molecule, which is H. Okay. So, therefore, the product of these two is the total flux across the surface. Okay. The heat flux for molecules that are moving downwards across the surface okay, is because of molecules which originate at a distance approximately of the order of a mean free path above the surface, okay, at a distance that is approximately b times lambda. Okay. Therefore, the flux of molecules coming down through the surface is going to be equal to z plus b lambda into h at z plus b lambda. Note that when there is a temperature variation, then the root mean square velocity also changes. Okay. So, therefore, this is the flux of molecules coming from above to below from a distance that is on average b lambda above the surface. Similarly, the flux of molecules going up through the surface is equal to some coefficient times Vrms at z minus b lambda into the enthalpy per molecule at z minus b lambda. Okay. So, that is the molecules that are going downward through the upward through the surface. Okay. Okay. So, therefore, the total flux okay, Qz is the molecules going upwards minus the molecules going downwards. Okay. So, that is going to be the net flux. Now, if the mean free path is small compared to the macroscopic scale, in this case the macroscopic scale is the length scale for the variation of the temperature. Okay. In this case the macroscopic scale is the length scale for the variation of the temperature. So, if the mean free path is much smaller than the length scale of the variation of the temperature, then I can use an expansion for each of these terms. Okay. So, for example, okay, Vrms at z plus b lambda is equal to Vrms at z plus b lambda d Vrms by dz at z. Okay. And Vrms is related to the temperature through this relationship. Okay. So, this is going to be equal to Vrms at z plus b lambda, okay, times d Vrms by dt times dt by dz. And because the Boltzmann constant is a constant, the mass of the molecule is a constant. So, the variation in the root mean square velocity is only through the variation in the temperature, okay, with distance. Okay. And you can easily verify this. Okay, this will be equal to Vrms at z plus b lambda Vrms by 2t dt by dz at z. Okay. dVrms by dt is proportionally t to the half. So, the derivative is half times Vrms by t. Okay. And similarly, you can also write h at z plus delta z and the rate of change of enthalpy density with z, okay, is just equal to h of z plus b lambda rho Cp dt by dz, okay, because delta H is equal to rho Cp times delta T, okay, where Cp is the specific heat at constant pressure. Okay. So, these are the relations that relate the values of Vrms and H at Z and Z plus delta Z, okay, through the enthalpy density and the root mean square fluctuating velocity. Okay. So, these expressions can now be substituted, okay, can now be substituted. Okay. So, therefore, Qz is equal to Ae into Vrms at z times H at z. Okay, so, this is okay, plus okay, b lambda into d by dz of Vrms H. Okay. I am sorry, the first term has a negative sign in it. Okay, the first term is coming from below, so it has a negative sign in it. So, I should be careful here. Okay. That is this first term here, okay. That is this first term here. And the second term is for the molecules that travel from above to below. Okay. So, this term will be minus of Vrms H at Z plus B lambda d by dz of Vrms H. Okay. And you can see that this first term will cancel out, okay, and I will get this as equal to AE. Okay. There is a negative sign here and there is a negative sign in front of this. So, I will get minus 2 AE B lambda d by dz of Vrms H. Okay. And if I substitute that the enthalpy density is equal to rho Cp T, okay, and dH by dz is equal to rho Cp dt by dz, and d Vrms is equal to Vrms by T dt by dz. Okay. So, I substitute these two and I will get minus 2 AE B lambda into 3 by 2 Vrms rho Cp dt by dz. Okay. So, you can expand it out and substitute it in check, and this is what you will get. Okay. And if I collect all terms here, I will get minus 3 AE B lambda rho Cp Vrms dt by dz. This is the flux from Fick's law of diffusion. Okay, this is the flux from Fick's law of diffusion. Sorry, Fourier's law of heat conduction. Okay, this is the flux from Fourier's law. If I write this from Fourier's law as minus k dt by dz, where k is the thermal conductivity, then this is what I get for the thermal conductivity. Okay. Okay, this is what I get for the thermal conductivity, okay, which means that the expression for the thermal conductivity for a gas is equal to 3 AE B Vrms lambda rho Cp. Okay. Okay. So, it is some proportionality constant of order 1 times Vrms times lambda times rho times Cp, that is the thermal conductivity for a gas. Okay. And the thermal diffusivity is defined as k by rho Cp, okay, which is 3 AE B Vrms lambda. Okay. So, the thermal diffusivity is also some constant times the mean free path times the molecular fluctuating velocity in a gas. Okay. So, the thermal diffusivity and the mass diffusivity are both proportional to the mean free path and the molecular fluctuating velocity. And the reason is because the mechanism of thermal and mass diffusion in a gas are the same. It requires the either thermal or mass diffusion across a surface in a gas requires the actual physical motion of molecules across the surface. Okay. Okay. Whether it is mass diffusion or thermal diffusion in a gas, it requires that a molecule actually cross the surface and carry with it the solute or the energy. Okay. And because the mechanism is the same, the diffusion coefficients have the same dependence on the mean free path and the molecular and the root mean square fluctuating velocity in a gas. Okay. The coefficient in front is different in general, but the expression is exactly the dependence on the mean free path and the root mean square fluctuating velocity is exactly the same. Okay. So, to within a proportionality constant, we have got an expression for the thermal conductivity or the thermal diffusivity. In a gas, the diffusivities are all the same because the mechanism is the physical transport of molecules across the surface. Okay. You can get a more exact expression for a hard sphere gas. Okay. Okay. The thermal conductivity is 25 by 32 molecular diameter square, okay, 1 by gamma minus 1, okay, into Kb cubed T by pi times the molecular mass whole power half. Okay. That is the thermal conductivity, where m is the molecular mass, dm is the molecular diameter, Kb is the Boltzmann constant, gamma is equal to the ratio of specific heats, Cp by Cv. Okay. The ratio of specific heats, Cv, is 3 by 2 K for a unimolecular gas, because there are 3 degrees of freedom. Cp is Cv plus K. Okay. So, you get 5 by 2. Okay. So, for a gas, for a unimolecular gas, Cp by Cv is 5 by 3. Bimolecular gas with 2 rotational degrees of freedom, Cv is 5 by 2, Cp is 7 by 2, and therefore, ratio is 7 by 5 and so on. Okay. So, with this expression for the ratio of Cp by Cv, you can get an estimate for the thermal conductivity in a gas based on the molecular diameter, okay, and the molecular mass. Okay. So, let us examine how this compares with the actual thermal diffusivity in a gas, okay, in air, for example. Okay. Okay. This is diatomic. Nitrogen and oxygen are diatomic molecules. They have 3 degrees of translational and 2 degrees of rotational freedom. The vibrational modes are not excited at normal room temperature. Okay. It is a diatomic molecule with molecular weight 29, okay, and molecular diameter approximately 3.7 angstroms. Okay. It is in the range 3.7 to 3.8 angstroms, the hard sphere molecular diameter for air. Okay. So, now I need to find out what is the molecular mass, okay, the molecular diameter is given, and the ratio of specific heats. Okay. So, the molecular mass is 29 grams or 0.029, okay, in kilograms is the molecular mass, okay, divided by 6.023 into 10 power 23 moles. Okay. Molecular weight in grams, you have to use the Avogadro number for moles. Molecular weight in kilograms, you have to use the Avogadro number for kilomoles. Okay. So, in this case, we took the molecular weight in grams, and therefore, the Avogadro number is in moles, and the ratio of these two is 4.82 into 10 power minus 26 kg. Okay. The ratio of specific heats, okay, the specific heat per mole for a gas, okay, sorry, specific heat per molecule for a gas, okay, Cv for a diatomic gas, okay, is equal to 5 by 2 kb, okay. Cp is equal to 7 by 2 kb, okay, which implies that gamma is equal to Cp by Cv, which is 7 by 5. Okay, it is a dimensionless number. And K, we have the formula here. So, this is equal to 25 by 32 into 3.7 into 10 power minus 10 meters the whole square into k 1 over gamma minus 1. Okay. So, 1 by 7 by 5 minus 1, okay, that is 1 over gamma minus 1. So, this 2 by 5. So, I will get a factor of 5 by 2 there, okay, into kb cubed. So, 1.38 into 10 power minus 23 joules per kg per Kelvin, sorry, joules per Kelvin, that is the Boltzmann constant, whole cubed into 300 Kelvin, okay, standard temperature and pressure, divided by pi into 4.82 into 10 power minus 26 kg, whole power half. Okay. And you can work this out, and the final answer turns out to be 0.032 watts per meter per Kelvin. Okay, so, this is what is given by this expression if air is considered a hard sphere molecular gas. Okay. The actual value is usually reported to be 2.6 to 2.8. Okay. Watts per meter per Kelvin, okay, in air. Okay. So, this is certainly the order of magnitude is certainly correct, and the quantitatively it is also reasonably accurate. Okay. It gets it to within about 10-15% the estimate for the thermal conductivity, assuming that air molecules are made up of hard sphere molecules with an average molecular weight of about 29. Okay. So, this kind of an expression can be used to determine the thermal conductivity in air. Okay. So, to summarize, as far as thermal conductivity is concerned, the mechanism is the same as mass diffusivity. Energy is transported because of a physical transport of molecules across a surface. When there is a temperature difference, there is a variation in the enthalpy density across that surface. There is a variation in the root mean square velocity also across that surface. Okay. And so, if you take into account the variation in the enthalpy density and the root mean square velocity and the physical picture that molecules that are going upwards come from a distance comparable to the mean free path below the surface, molecules going downwards come from a distance comparable to a mean free path above the surface. Do the same calculation, assume the mean free path is small compared to the macroscopic scale, and express the velocities, root mean square velocity and the enthalpy density in a Taylor expansion, a Taylor series expansion. Right. Then you will get an expression for the heat flux, in which the thermal conductivity is equal to Vrms into the mean free path into rho Cp. Thermal diffusivity is just Vrms into lambda. Okay. So, it has the same dependence on molecular properties as the mass diffusivity. Okay. And I gave you a more exact expression for this, which involves the ratio of specific heats Cp by Cv. So, this is thermal conductivity in gases and thermal diffusivity in gases, which the thermal diffusivity is of the same, has the same dependence on the mean free path and the root mean square velocity as that for mass diffusivity. Next, we look at thermal diffusivity in liquids, and then we will progress to momentum diffusion. Okay. I will first complete a little bit on thermal diffusion in liquids in the next lecture, and then I will proceed to momentum diffusion in liquids. I will see you in the next lecture.